Hey, chemistry, how you doing? We are up for another flipped lecture here. I hope you're excited about it. I'm excited about it. We're studying stoichiometry today. Love that word, stoichiometry. It's as much fun to do as it is to say. I hope you agree. It's just basically chemistry math, but it's not very hard. So here we go, jumping right in. Consider the following reaction. We have carbon dioxide plus water making sugar, and oxygen gas as a byproduct. This is photosynthesis, right? Okay, photosynthesis balanced is 6 CO2 plus 6 H2O, yielding 1 sugar molecule plus 6 O2. Okay, it's important to have those sixes there. How many moles of carbon dioxide does a plant need to absorb to make 1 mole of sugar? The answer is 6. I will show you why I know. Here we have a coefficient that's assumed to be 1. There's not a coefficient, it's 1. And here we have a coefficient in front of the CO2 that is 6. And so what you can do with a balanced chemical equation is you can look at all the coefficients here in front of all of the terms, and you can use that to build something called a coefficient bridge, which is a ratio relationship of how many of these different molecules are needed to make the reaction happen. Okay, this is a molar ratio, and so the moles are related to each other in a way that is predicted by the balanced chemical equation. So once again, the moles are given to you in the balanced chemical equation. It allows you to predict the number of moles of reactants needed to complete any reaction, or the number of moles of product that you expect to get out of a reaction. Okay, so this is a way of setting your expectations beforehand as a chemist to see, well, I'm going to need this much of these things to get this much of these things. Okay, you can then use the mole mass relationships to determine the mass of reactants or products. So you already know how to use molar mass and convert from masses to moles or moles to masses, and now you're going to be able to do that and use this coefficient bridge so that you can say, I need this many grams of A and this many grams of B, and I should get this many grams of C and D when I'm done. All right, that's what we're doing here. So look at several examples. If a plant has 3 moles of water available, how many moles of sugar can it make? Well, let's look. So this is a coefficient bridge here. There's a relationship of 6 moles of water to 1 mole of sugar. Okay? So that's the ratio, 6 moles of water to 1 mole of sugar. I've been told that I have 3 moles of water available. Use bridge notation, 3 moles of water, and the relationship is 1 to 6 moles of water to moles of sugar. Put the same thing that you've got as this term on the bottom so that they cancel out, right? Multiply across and divide. 3 divided by 6 is 1/2 or 0.5. So you have half of a mole of sugar that you've made from your 6 moles of water. Okay, the plant could make 0.5 moles of sugar. Another way of doing this, if a plant produces 18 moles of oxygen as a byproduct, how much sugar was made? So we're going to do the same thing. Look at the coefficient bridge, 6 to 1. Okay, the molar relationship is 6 moles of oxygen to 1 mole of sugar. 6 moles of oxygen to 1 mole of sugar. So again, I have 18 moles of oxygen, bridge notation, put the like term on the bottom so they cancel out. 18 times 1 divided by 6. 18 divided by 6 is 3. I have made 3 moles of sugar. Okay. One more example on this. If a plant has 24 grams of water stored for the purpose of photosynthesis, how much sugar can it make? So now I need to use the molar mass of water to get the moles of water, and then I can use the coefficient bridge to determine how many moles of sugar I can make. So I need to determine the number of moles of water. Water's molar mass is 18, I'm rounding here, 16 plus twice 1, right? 2 times 1 for the hydrogen, 16 for the oxygen. Molar mass is 18 grams. I have 24 grams of it. 24 grams divided by 18 grams per mole, I get 1.333 moles of water. So that's what's going in. Now I need to have my coefficient bridge, 6 to 1. And 1.333 moles of water, moles of sugar, cancel out my like terms, multiply, cross, and divide. 0.222 moles of sugar, okay, but yeah, so, oh, look at that, my decimal point didn't travel. 0.222 moles of sugar is my answer. I was given 3 sig figs, I report as 3 sig figs. So I can make 0.222 moles of sugar from 24.0 grams of water. All right. Now, theoretical yield versus actual yield. This is very important if you're actually an industrial chemist and you're making a product. You work for Bayer and you're making aspirin. You need to be able to determine how efficient your processes are. You don't want to waste anything. Your reactants cost money and your products are what you sell. So let's not waste stuff and let's not run out of things, right? So theoretical yield is on math, paper, how much of this should you make? The actual yield is what you actually make, and then you can compare the two and determine how efficient your processes are and hopefully find where you're losing things along the way. The formula here is actual divided by theoretical times 100% gives you percent yield. It's very much like percent error. Percent error would be theoretical minus actual divided by theoretical times 100%. That'd be percent error, and you can get the one from the other really easily, and you'll see that here in a minute. Okay. So in the previous example, if you actually made 0.213 grams instead of the 0.22 you were supposed to, what's your percent yield? Well, actual divided by theoretical, so actual divided by theoretical, and that gives me 0.95945, and I'm going to multiply that by 100%. Gives me 95.945%, but I need to correct for sig figs, so I have 95.9% because I have 3 significant digits here. The plant was therefore 95.9% efficient. So if you wanted to say what's your percent error, right, you just subtract that from 100%. And you would say, oh, my percent error was 4.1%. All right? All right, last concept, limiting and excess reagents. So if you have an excess of something and not enough of something else, then the thing that runs out first in the chemical reaction is the limiting reagent or limiting reactant. And the reaction will then stop because there's not enough of something to keep it going. So if I'm burning a match in a room, the room is full of oxygen and my match is the only little bit of fuel. I could burn the match until the wood is all gone, and then I would still have oxygen in the air. If everybody in the room died watching the experiment, then I burned up all the oxygen, but probably not going to happen. So the wood would have been the limiting reagent. The oxygen in the air was in excess. There was an abundance of that. So again, industrial chemists doing this for a profession, trying to make something to sell, we have to make sure that we've got enough of all of the ingredients to make the reaction happen, and we don't want to run out of something and have leftover something else. So stoichiometry helps an industrial chemist balance his reaction and know how much of all these things to put together so he's not wasting his money on ingredients. Okay? So to calculate a limiting reagent, we use a coefficient bridge, we use molar mass ratios, and we look at the relationship we're supposed to have and make sure that that's the relationship we actually have. And we can identify what, if anything, we need to add to make the reaction keep going. Okay, let's do an example. If the plant were in a greenhouse with 184 grams of CO2 in the air, and it has 19 grams of water in its tissues and in the soil, 19 grams of water available to it, what's the limiting reagent? Now, this is not an industrial chemistry problem, but you can see in this example we've kept using the same equation to hopefully make you comfortable with this concept. So which reactant is limiting and which reactant is in excess? Here's my two reactants. I've got a ratio of 6 to 6. They should have the same number of moles. Let's see what I've got available to my plant. So CO2, molar mass is 12.01, right? And then water is, I'm sorry, 12.01 is the carbon, and 2 oxygens gives me 14.01 grams per mole. Okay, so 44.01 grams, I have 184 grams of it. Do the division, and I find out that I have 4.1809 moles of CO2 available to me. Okay, same thing for water. 16 for the oxygen plus 2 times 1.01 for the hydrogens gives me 18.02 grams per mole. So if I have 19 grams of that divided by 18.02, I have basically 1 mole of water. Look at the coefficient bridge. 6 to 6 is basically the same as 1 for 1. So I should have as much CO2 as I have water as far as their molar ratios go, but I don't, right? So I've got a lot more CO2 available than I do water. So water is the limiting reactant. It's going to run out first, and I will have CO2 that's in excess. All right? I hope that you understand. If you don't, that's okay. Shoot me a question, and I'll answer it as quick as I can, or see me in class tomorrow. We're going to do so much stoichiometry for the rest of this year. You're going to just eat, breathe, and sleep stoic, and it's going to be coming out your pores. So don't worry about it if it doesn't come up right away in your brain. You will get this, okay? I believe in you. Jesus loves you, and so do I. I will see you tomorrow. God bless.